with that as a healthy preamble, let's move on to a quick example of implementing Poisson regression in R, which actually turned out to be relatively straightforward. What I'm going to do is I'm going to bring in a little code that I have from one of my slides. And as an example, I'm going to use a traffic fatality study that comes in the package called AER. AER stands for Applied Economics in Econometrics in R, I believe, or something along those lines. I'm not going to install it. You can install it with this. I am just going to bring it into my session with the library command, and it brings in a data set called fatalities, which I'm going to bring in with the data function. And if we want to take a look at what the fatality data set is, we could look right here and make this a little bit bigger. It's a set of U.S. traffic fatalities for the lower 48 U.S. states from 1982 to 1988. What we're interested in is the count of traffic fatalities in each state by year over that time period, and the effect of a beer tax and mandatory jail time. So basically, we're looking at the effect of enforcement and economics on injury prevention. And I have really not seen the study that these data came from, so I don't know whether this makes any sense or not, but it really is simply intended as an example to how to implement practically a Poisson regression model in R. It really might not make a whole lot of sense to do it this way, but let's just do it anyway. So we've brought the data set in here. We can take a look at the structure of the data set itself. It's a big data set. There's a lot of stuff here. We've already seen the help page for the data set. There are 336 observations of 34 variables. It's basically, 48 states by 7 years and 34 variables. That kind of makes sense. So, first thing we're going to do, as we should always really do, is let's just take a look at the data. What I have here, let's just look at it in terms of descriptives and stratified analysis, that kind of stuff. I'm just going to do something really quick here in the interest of time. Let's just take a look at the incident rate of motor vehicle crash by state and year. And it's kind of a simple thing to get at that, if you know a little bit about R processing. I'm going to create a table called Table of Deaths. Then I'm going to create a table called Table of Exposure. And I'm going to use the tapply function to do that. I'm using with here. You don't have to. This is just so I don't have to write fatalities and use the $ notation. But basically, this is the real nuts and bolts of it. I want to stratify the sum of the number of fatalities by state and year. And if this code doesn't make sense to you, you can just go back to some of the data manipulation slides on this in this course. So let's just create that data set, that table right there. And it also brings it up here. So these are the counts of fatalities in each state, Alabama down to Wyoming, for the 7 years of data, 1, 2, 3, 4, 5, 6, 7, 1982 to 1988. Do the same thing. There's a variable called total miles, and total miles, or miles total, is the total number of millions of vehicle miles driven in that state. And we're going to use that actually as the denominator for this data. And we're going to end up using it as the offset variable in the Poisson regression. Simple matter to calculate the number of fatalities per 100 million vehicle miles. We just divide the table of deaths by the table of exposures and multiply that by 100. We have this table now, which is really just like a simple calculation here that R can do for us. So here are the incidence rates per 100 million vehicle miles driven. And always helpful to look at things graphically. I'm just going to use the plot TS, which is a time series plot. It's actually very nice if you have data that you want to plot across some sort of like time series. You could do that. I'm using this little T here to transpose the data set because by default the time series data set basically plots the longer series by the shorter series. So it would be like a time series across. Basically, it would put states on the x-axis and just and not the time on the x-axis. But this gives us what we want. We can take a look at what it looks like here. Just going to bring it over here, and what we are looking at is the incidence rate per 100 vehicle miles driven in 48 states from 1982 to 1987. What is it, 87 to 88? right here, those 7 years worth of data. See a couple of things, a lot of variation, maybe more variation than would be allowed for in a Poisson regression model, and that's an important feature. As I said very early on, one of the underlying assumptions of a Poisson distributed variable is that the mean is equal to the variance. That assumption is not always met. If it's not met, your standard errors may be a bit too liberal, and you may end up getting statistically significant results when in fact they aren't statistically significant. And in that setting, folks recommend things like negative binomial. I'm not going to go into it, but anyway, you do see a lot of variation here. You also do tend to see this, there is this clear sort of trend, right? I think this sort of declining trend and this decreasing in variation over time, and that's kind of interesting in and of itself from a time series perspective. But what we are going to do is run a series of Poisson regression models, and I am again just going to grab a little syntax from one of my slides, and the slides are on the website as well. And here is the syntax for a couple of things. What we're going to do is we're going to run a model that includes just year as an explanatory variable. And then we're going to look at the structure of that model and look at a summary of that model and show how we can easily exponentiate the coefficients from that model. We are also going to look at two or three other models. And the first one is going to be one that includes state. Then there's going to be a model that includes jail time, and then a model that looks at beer tax, and we can take a look at all those. So the first thing is just running a regression model. We're going to look at year, just the effect of year. We saw from the graph that clearly year had some sort of effect, right? And it should. And the way we specify the model is generalized linear model. Outcome variable is fatalities. The year variable is our single exploratory variable. There is an offset option to specify our offset variable, in this case it's going to be the log. It should be the log of the vehicle miles driven in millions of miles. We specify the family as Poisson, and I'm trying to see what exactly I'm leaving out. Oh yes, and we have to specify the data, which didn't come across. Data equals fatalities. That didn't come across when I cut and paste, so make sure you get that. And if we run that, runs relatively quickly, we can look at a summary of this model here. Summary is really a very concise, straightforward representation of the model. It tells us the call, just to remind us, gives you a little information about the deviance. Deviance is the sort of like residual analog for GLMs, where you really can't calculate residuals, which require a linear model. And here we start seeing the beta coefficients. Remember, all of this is on the log scale. Each one of these is basically, if we're looking at the count of fatalities by millions of vehicle miles, each one of these is basically 1 unit increase in year here from 1982 to 1983. 1982 is the baseline, results in a 0.7 or so increase on the log scale in that rate. And we see that basically there is this trend of decreasing risk. Of course, humans don't work really well on the log scale. It's relatively straightforward to exponentiate. One thing you could do, you could always just bring up the model itself with the structure command, and we see that there are a lot of things in this model over here, one of which is coefficients. Where is it? It's over here somewhere. But there is one of the bins in the list called coefficients. There it is, the very first one, coefficients. And these are our coefficients that we saw there. And we could just simply use the fact that it's a named list and that this regression object is a named list, and exponentiate that particular part of it, and we get the exponentiated coefficients. Or we could take advantage of the convenience function coef and just exponentiate that. This is what we've been doing with our regressions all along. And we could just take a look here and see, okay, so each year compared to the baseline year has a decreased risk. And these are interpreted like incidence density ratios. So, for example, in 1986, it's basically a 10% lower outcome risk of crash in terms of the number of crashes per million vehicle miles traveled. And if we want to know whether that is statistically significant, we can use the confidence interval function and exponentiate that. and we get our confidence intervals for each one of those. And we see that the effective year was pretty clearly statistically significant across the board. Of course, assuming that the Poisson regression is a good way to go. Now, one thing I'm just going to bring up the summary one more time just to show you something here. In terms of model fit, there's a couple of different ways to look at model fit. One thing is you could look at the Achim information criterion comes up. It's a relative measure, so it doesn't really mean anything in and of itself right now. We're going to compare it. This is kind of useful. Okay, so the null deviance here is 12,293. We would expect that, just because of noise, to go down by the number of variables. But we see there's a bit of an effect of the of adding year here. You know, if year added, if these variables added nothing, it would really only go down like 6 or 7 units or so, and it went down much more than that. So year had an effect. It helped the fit. We can look at another model now, and again, I always forget to take this with me. What I want here are make sure that we specify the data equal fatalities over here. And this is just a mistake I made from cutting and pasting it. But if we have that right there, we could run Model 2. Hopefully that'll run. And let's take a look at a summary of Model 2. Well, one thing we see right away is that AIC, the Achim information criteria, came down quite a bit. So adding state really helps explain a lot. It really is a much better fit here. I'm trying to bring it so it went from 14,300 to 4679. That's a big improvement. Also, adding state decreased the residual deviance much more than would be expected just from noise. So that's a good thing. We're not really interested in the effect of any individual state, to be perfectly honest. I'm just putting it in there mostly for model fit, and also because there is enough variation across states. I think it's important to keep it in there. Let's see what the effect is of including jail time in a state. If a state had a jail sentence, and again, I just need to add this in here because I forgot to do that. But let's take a look at a model that has year, state, and jail time and see what kind of effect that has. And of course, that didn't work out well. Let's see. Did it run? It did run, right? But what's happening here is this. There you go. So we can take a look at a summary, see if it improved things at all. And AIC came down a little bit more. Not a whole lot more, a bit more, enough to sort of like perhaps justify keeping it in there. And if we were to look at the exponentiation of the coefficients for this model, and we see here jail time had some sort of effect, but it looks like it actually increased the risk for some reason. Chances are that's probably not statistically significant. We could just look right here. If you notice, right here is the standard error. And if you see here that this is probably not statistically significant just from looking at the standard error, but we could always just exponentiate it. And if we go down here, if we're exponentiating, model 3. Exponentiate model 3. And we see that jail time, you know, if we want to, we could say it increased it by some, but I'm sure if we look at the 95% confidence intervals, we'll see that, it takes a moment for this to come up, we'll see that it probably is not statistically significant, and it's really just about 1. So jail time, having jail time in a state doesn't really seem to affect the risk of injury at all. Let's see if charging more for beer has some sort of effect on the risk of motor vehicle crash injury. And of course, I'm pretty sure you know where this is going. It's pretty much going to. But let's just, I've done this already. So we look at a summary of the model, adding that variable for beer tax actually improves AIC even more. So it's even better fit. If we were to exponentiate those coefficients, what would we find? Look at this now. Having a beer tax apparently decreases the risk almost 25%. And is that statistically significant? Yes, it is. I'm sure it is. I'm waiting for it and of course it is. Anywhere between sort of like 30 and 20%, it decreases the risk of motor vehicle crash injuries. So that is Poisson regression in R. I think it's kind of an interesting example of how, for this particular one, of how economics sort of trumps law enforcement in some public health outcomes. But it's a relatively simple and straightforward matter to implement Poisson regression in R. The difficult part, as always, is understanding what you're doing and trying to make sense of the data themselves. As I've alluded to a couple of times, Poisson regression might not be the most conservative approach to data. There are different approaches to doing that, including negative binomial and quasi Poisson regression. And I'll leave it to you to explore those.